In this video, we're going to have a look at resultant forces as also dealing with them in terms of moments. So quite a lot of information here. Let's break it down. It tells you there's a container of mass 22,000 kilograms. That container is acting at this point here. It tells you when the container is being raised, the center of mass is at a horizontal distance of 32 meters from this pillar PQ. So this distance from here to here, as it's labeled here, is 32 meters. Assume the tension in each of the 4 lifting cables is the same. It's referring to these 4 cables here, by the way. They all have the same tension. It's then told you to calculate the tension in each cable when the container is lifted at a constant velocity. So that there is very important, the fact that it's moving at a constant velocity. It's not speeding up and it's not slowing down. That means that its acceleration is 0. What equation links to acceleration? Well, it's F equals ma. If acceleration is 0, that means F, which stands for resultant force, is equal to 0. It's very important that you remember that this is the resultant force and not just the force. What that means is that the combined weight of the container is being balanced by the upward tension of all of the 4 pillars. So let's call that 4T, because all of them have the same tension of T. So if we find the weight by taking the mass of the whole container and multiplying it by g, because weight is equal to mg, we can make that equal to 4 times the tension, and then we can divide both sides by 4 to get the tension itself. Again, we're using the fact that resultant force is 0, so we can say that the upward forces are all balanced by the downward forces. Let's find that weight first. Weight is equal to the mass of 22,000 multiplied by g, which is 9.81 meters per second squared. So if you do A-level maths, you may have used 9.8. So just a quick reminder that in A-level physics, you want to use 9.81. That will be a value of 2.16 multiplied by 10 to the power of 5 newtons. And like I said before, we make that equal to 4 times the tension. You then divide both sides by 4 to get that the tension is just equal to 5.4 times 10. So let's first write out actually. It's equal to a quarter of the weight. So it's equal to 5.4 times 10 to the power of 4 newtons. Great. Let's move on. I think we're probably going to have to use this later on. Calculate the moment of the container's weight about the point Q. Okay, so what is a moment? A moment is the force multiplied by the distance of the force from the pivot. One very important thing to note, the force has to be at 90 degrees to the surface that it's acting on. In this case, if we're dealing with the weight created by this mass, it is at 90 degrees to this distance, so that's completely fine. What we do is we take the force due to the weight, which is this value here, 2.16 times 10 to the power of 5. You multiply that by the distance of where the mass is located from the pivot, which is 32 meters, and you can make all of that equal to the moment. So let's do that. When you do that in your calculator, you get 6.9 times 10 to the power of 6 Newton meters. If you guys would like, just let me know in the comments and I'll go through a question where the distance is actually, the force is not perpendicular to the distance. So you have to take the component of the force that is perpendicular by using SOHCAHTOA. It then asks you to describe and explain one feature of the crane that prevents it from toppling over when it's lifting. So what is preventing it from toppling over? What is making it travel at this constant velocity? Like we mentioned, the resultant force is 0, so the upward forces are balanced by the downward forces, but also the fact that it's in equilibrium is because it means that the moments are balanced. What I mean by that is we say that the clockwise moment that is created by the mass here, because remember if we pick this as our pivot, then this would create a clockwise moment, is balanced by the anti-clockwise moment created by this counterweight that's put on the left hand side. So because those moments are balanced, that's what's keeping it in equilibrium. If one moment was larger than the other, then it would turn towards that larger moment. If the moment created by this mass is larger than the moment created by this counterweight, then it would turn clockwise, following the direction of the mass itself. Let's summarize that in a few set phrases. We can say that the moment, or even to be even more specific, the anti-clockwise moment created by the counterweight is equal to the clockwise moment created by the mass, the 22,000 kilogram mass that was initially introduced. If you want to be even fancier, just to secure those marks, you can then say net moment is 0, or you can even say the fact that it's in equilibrium. And yeah, if this was the 3-mark question, then that additional statement would get you that 3rd mark. Great, let's now move on. It tells you each cable has a cross-sectional area, so we're actually moving on to materials now. Cross-sectional area of 3.8 times 10 to the minus 4. Sorry if you guys couldn't read that. It then asks you to find the tensile stress in each cable. Well, what is tensile stress? It's actually the force experienced by each cable per unit cross-sectional area. So what is the force experienced by each cable? Well, it's actually the tension in the cable, which we've previously calculated, 5.4 times 10 to the power of 4. So we take that force and then we divide it all by the cross-sectional area, which is 3.8 multiplied by 10 to the power of minus 4. Let's do that on the calculator. Oh, wait, I've already done it. And it's 1.42 times 10 to the power of 8. I don't know if you guys remember the units. It is actually pascals, but if you didn't know that, a little trick with A-level physics. Since we're doing force, which is newtons, divided by area, which is meters squared, you can also say the area is newtons per meter squared, or nm to the power of minus 2, if you want it to be fancier. Lastly, it's told you just before the container is shown in the diagram above was raised by the ship, the length of each of these cables was 25 meters. Show that each cable extended by 17 millimeters when it was raised from the ship, and it tells you the Young's modulus. Well, let's break this Young's modulus equation down to make extension of the subject. We know Young's modulus is stress divided by strain. We also know stress is force per unit cross-sectional area. We know strain is extension over length. By the way, for extension, you might have seen the word little e or change in length. Whatever just suits you, you guys can use that. Breaking this down, we say the Young's modulus is force over area divided by extension over length. Whenever you divide by a fraction, that's the same as multiplying by the reciprocal of that second fraction. And so we can say Young's modulus is equal to FL over AX. If we now replace the positions of extension and Young's modulus, we actually get that the extension is FL, force times length over cross-sectional area multiplied by Young's modulus. And this helps us find the extension. We already know the force experienced by each cable. That's just the tension that we introduced beforehand of 5.4 times 10 to the power of 4. Let's write that down. We also know the length of each of these cables. It's 25 meters. We divide all of that by the cross-sectional area, which is mentioned here. Sorry, I forgot about that for a minute. 3.8 times 10 to the minus 4 multiplied by the Young's modulus that's given us on the bottom of this question, which is 2.1 times 10 to the power of 11. Again, I don't know why this power is so small. That is 10 to the power of 11, by the way. Put all of that into a calculator and you'll get 0.017 meters. And then to turn that into millimeters, you multiply by 1,000. So that's 17 millimeters. And that's the answer for this question. Quite a few parts to this. There's a bit of moments, a bit of resultant force equals 0. But just in general, whenever a system is in equilibrium, you say the resultant force is 0. And you say clockwise moments are balanced by anti-clockwise moments. Those are the two main ways you go about doing these questions. If you like the video, please be sure to leave a like and subscribe. I'll appreciate it a lot. Thanks for watching.